the first part is on low temperature refrigeration systems, two-stage refrigeration systems, cascade refrigeration systems, and a system used for the liquefaction of gases. And another part on non-conventional refrigeration systems. I will talk about absorption refrigeration system and the Vortex Tube. If you remember yesterday, we have about the first or single stage refrigeration cycles. I said that they work on two pressures. This is the evaporator pressure, and this is the condenser pressure or temperature. So here is the compressor. We define a pressure ratio which equal to the ratio of the condensation pressure on the evaporation pressure. When this parameter increase, the efficiency of the compressor decrease. It means the efficiency of compressor vary like this with the pressure ratio of the compressor. What does mean that the tau increase here in the cycle? You follow with me? What does it mean when tau increase? It means that P condensation increase or P evaporation decrease. I told you that the temperature of condensation has a relation with the environment. It means it is constant. So the increase of tau is due to the decrease of the temperature of evaporation or pressure of evaporation. It means to cool at low temperatures. You understand? To cool, to have application at low temperature. Generally, when tau is greater than 8, you may find in some books 9, it is not economically practical to produce cool with a single stage cycle. We have to do another system like two-stage refrigeration cycle or cascade refrigeration cycle. So in the same application, when I have, for example, a two-stage refrigeration cycle like this, this is between the evaporation, condensation here, and there is an intermediate temperature. So this is a two-stage. If I run in this condition on one stage, it may be this cycle. So if to pass from single stage to two stage, I have this save of energy consumed by the compressor. It's clear? So I repeat, for single stage refrigeration cycle, it works on two levels of pressure. The high pressure for the condenser and the low pressure for the evaporator. When the pressure ratio defined here as tau, the ratio between condensation pressure and evaporation pressure increase, it means that the pressure of evaporation decrease. It is not economically practical to produce cool with a first stage. We have to pass to two-stage or another system, cascade stage. So generally, single-stage refrigeration systems are used to obtain temperature or cooling temperature between 10 and minus 30. And for temperature lower than minus 30, it is necessary to use a two-stage refrigeration cycle or a cascade refrigeration cycle. So the increase of tau may make many harms, like the decrease of the efficiency of the compressor, first. The second point is the increase of the discharge temperature. And the third harm is the increase of the energy consumed by the system. So generally, multi-stage refrigeration system or two-stage, for a two-stage, for example, we can reach a temperature of minus 65 degrees, and we can reach minus 100 degrees with a three-stage. And in the cascade cycle, we can reach temperature lower than minus 80 degrees, minus here, 80 degrees. And it is also possible to use, for example, cascade refrigeration cycle to liquefy natural gas. So we reach minus 160 degrees. This is a simple two-stage refrigeration cycle. It is composed of a low-pressure compressor, a high-pressure compressor, a condenser, an evaporator, two throttling valves, and a flush tank. So if we, for the calculation of the cycle, we have already talked about thermodynamic properties of the refrigerant. Here, one refrigerant is used. We use only one refrigerant. So we have equation or tables or diagram to get thermodynamic properties. Then we apply the energy balance to each component of the system to get the energy consumed by the compressor, the heat exchanged here in the condenser, in the evaporator, and for the throttling valve, the enthalpy is constant. So in this table, we have mass balance and energy balance to get all the parameters used for two-stage refrigeration cycles and to get the performance of the system. We can use also the second law of thermodynamics through the exergy analysis, and we can put here another row for exergy balance. For energy balance is the first law of thermodynamics. Energy is conserved. The energy, the inlet equal to the outlet. But for exergy analysis, exergy is not conserved. Exergy at the inlet equal exergy at the outlet plus the destruction of exergy. So here there are the two levels of pressure: the low pressure in the evaporator, the high pressure in the condenser, and there is an intermediate pressure. This parameter, this pressure is a K parameter for the economy of the system. It means that there is an optimum value for this parameter to get the maximum coefficient of performance or the minimum of energy consumed by compressors. So there is in two-stage refrigeration system, generally they use for the selection of the intermediate pressure, they use this formula, P intermediate equal the mean, the geometric mean of P condenser, P evaporator. To select the intermediate pressure. And this formula has been obtained using the following assumption. First, for the assumption, both stages move the same refrigerant mass flow rate. It is not true. If we return here, for the first stage here, there is a mass flow rate M1, and here for the second stage, there is the mass flow rate here M1 plus the vapor that has been obtained here. When we throttle from 5 to 6, there is some refrigerant who is changed phase to vapor. So M2, the mass flow rate of the second compressor, the high pressure compressor, is greater than the mass flow rate of the compressor low pressure. The second assumption, the refrigerant behaves as an ideal gas. It is also not true. We have seen yesterday that an ideal gas should verify the three assumptions. First, molecules have negligible weight. The second one, absence of interaction between molecules. And the third one, an ideal gas obeys to the PV equal to RT. And all these assumptions are not correct here because there is the liquid phase, so interaction forces are increased. And the third assumption, the inlet temperatures of the two stages of the compressor are equal. It is also not true. So there are this formula. The pressure, intermediate pressure equal to the geometric mean of evaporation and condensation pressure has been elaborated on the basis of the minimum work consumed by the compressor. So for an ideal gas, the work is simply by this formula. This is for the first stage, this is for the second stage. And for the assumption, the first one, the temperature at the inlet are the same. So we can write this one. And to get the maximum, the minimum, we derive this quantity and equal to 0. And we obtain this formula for the intermediate pressure, which is not correct. So there are many other formulas that have been developed for particular cases are listed here. And in 1996, Zubair and collaborators has developed a method based on the maximum coefficient of performance. He varied the intermediate pressure temperature from the evaporation temperature to the condensation temperature and created another variable, theta, equal to T intermediate minus T evaporation, T condensation minus T evaporation. And he get like this, look up, the coefficient of performance like this. And the maximum here is correspond to the optimal intermediate temperature, and it is about here 0.5. It means the arithmetic mean of condensation and temperature and evaporation temperatures. We used in my PhD thesis, I used the same concept but using the exergy analysis. I tried to do the same thing, but instead of the COP, I had used the exergy efficiency and the the exergy, the total exergy losses. Exergy loss like this. The minimum will be around 0.5. It means around the arithmetic mean of condensation and evaporation temperatures.
Is this water yourself? That water is you, correct?
In my PhD thesis, yes. We have been inspired by the work of Zubair. We just used the exergy analysis, and we computed all exergy losses in the component, and the total exergy loss, it will be minimal in for theta equal to 0.5. Any question for student? Another way to obtain low temperature is the cascade refrigeration system. So here, the system, there are two single systems in this example. There are two single systems linked between them by a heat exchanger here. A high pressure system here that use different refrigerant. Another system, low pressure system here that use another refrigerant. So here we can benefit from the use of the characteristic of refrigerant. Refrigerant with high critical temperature can be used here. Refrigerant with low critical temperature can be used in the low pressure side. For example, we can use ammonia here because ammonia, the temperature is greater than 132. And here we can use carbon dioxide, which temperature is around 31 degrees. And we can calculate with the same thing the performance of the cycle, the coefficient of performance, and here the energy balance of the condenser that link the two systems. This system is used in commercial application, and it is used also for the liquefaction of gas, of natural gas. And the first plant was built in Algeria, used the concept of cascade concept to liquefy natural gas. But it is more complicated than this one. It is composed of three parts. We'll see after. 3 parts. A part with 3-stage propane cycle, another system for 4-stage ethylene cycle, and another system 3-stage methane cycle to obtain a temperature of minus 160 to liquefy natural gas. So there are, until now, 2 means to obtain low temperature systems. Multi-stage refrigeration system like 2-stage or 3-stage, cascade refrigeration, and there are another way to liquefy gases, and it is used to liquefy, for example, oxygen, azote, nitrogen.
Why do you prefer the cascade system instead of this in Algeria? Why do you prefer the first one, the cascade system, instead of Linde-Hapsan?
No, it is not Linde-Hapsan.
What is the reason for applying the first one in Algeria?
The first one was built in 1964 by a French company, Technip. 1964. Yes, 1964 by a French company, Technip. Then after, there were the American companies, APCI, and the most famous is APCI. So Technip can't conquer us with the company, the American company.
So do you mean the new ones are not cascade refrigerant
No, there are not a cascade.
They are this one.
No.
What types?
For natural gas?
Yes.
We'll see, we'll see. We'll see.
Thank you.
Yeah. Other question? So the other system, the other group of systems that are used for the liquefaction of gases, of industrial gases, like nitrogen, hydrogen, oxygen, are gas liquefaction cycles, like the Linde-Hampson cycle here, which is simply composed of compressor, heat exchanger, and here a flush. Generally, in this type of cycle, there are two parameters to take into account: the quantity of liquid obtained here, the quantity of liquid obtained at point 4, and the work consumed to drive the compressor. So the interest is to increase Y and to decrease W. And using the concept of the Joule-Thomson expansion here. There are another improvement of this cycle did by Claude, and it is composed of 3 heat exchanger, a compressor, and an expander. The expander here maybe produce work to drive the compressor for the economy of the system. The expander here, here when cooling from 2 to 3, we cool from 2 to 3, then here is divided by 2 parts. A part will continue to cooling in the heat exchanger, and another part undergoes an expansion process here in the Joule-Thomson valve and produce work. The work is not in an expander. In expander and produce work, the work can be used to drive the compressor for the economy of the system. And this one is used on board. Yesterday, someone called Morat write me on LinkedIn, asked for and he is working in Netherlands. He did his study here. He was working in Netherlands on a ship, and they use a system of reliquefaction on board ships. You know that when we transport liquid in tanks, some of the liquid evaporates naturally. So we remove the vapor, reliquefy the vapor, and return them to the tank for the security. Because when there is evaporation, there is increase of the pressure, and the tank is designed to support a designed pressure. So this system is used on board ships to reliquefy LNG, the boil off of LNG, and return it to the tank. And this is natural gas application. Here, another application, more complicated cycles that use technology, high-tech technology. This is, in this figure, you have the liquefied natural gas chain. So gas is produced, for example, in Algeria in the desert, then is transported by pipelines to liquefaction plants. Generally, liquefaction plants are near the sea, and then stored in tanks and shipped by LNG tankers to the customers, like, for example, Turkey buy natural gas from Algeria, liquefied natural gas from Algeria. So there are two main to transport natural gas. There are pipelines and tankers. So when the distance generally here, the cost of transport by pipelines, and here by at Liquefied by ships. So about 3,500 kilometers, it is economically viable to use ships to transport LNG. So when the natural gas arrives to the liquefaction plant, first it is treated. So in the treatment, we remove water from natural gas, we remove carbon dioxide, and we remove mercury. Then it enters from here, it enters the liquefaction plant. The first one, I said that the first one used concept for the liquefaction of natural gas was the concept of cascade system. Here, a simplified cascade refrigeration system, it is composed of three parts, a part of propane, a part of ethylene, and a part of methane. Then the propane is cooled by ethylene, and ethylene is cooled by methane in a cascade manner. So it was the first one. Then came more complicated system that use here. In the first one, we use pure refrigerants, propane, ethylene, and methane. But here we use, for example, for this technology of we use a mixture of nitrogen, methane, propane, and ethane. So the natural gas is first pre-cooled using propane. Then it is cooled in this main heat exchanger, using this mixture of 4 refrigerants. Another concept is the use of another mixture, but the mixture is used for both pre-cooling and for liquefaction. A mixture that is composed of nitrogen, methane, propane, ethane, and isopentane. So, and there is a cold box here to ensure the liquefaction of natural gas and to achieve a temperature equal to minus 160 degrees. Another one was developed by the companies Statoil and Linde. It used 2 mixtures, one mixture for the pre-cooling and another mixture for the liquefaction. So it is all for the low temperature, obtained low temperature using refrigeration systems. Any question or debate? Just yesterday, we talked about the thermodynamic properties of refrigerants. And I asked the question, for example, for when we heat water, for example, from 20 degrees to 100, and then the temperature will be constant, then it will increase. The temperature of vapor, it will increase. This is valuable for pure refrigerant. For mixture, it may be, the temperature may be with a glide here, maybe like this, for mixture. The phase change may be ensured with a glide, a temperature glide, for some mixtures. But for pure refrigerant, the phase change is at constant temperature and pressure. Any question?
What is MCR?
Mixed component refrigerant. Makes sense. So generally there are three steps in the liquefaction. There are pre-cooling, then liquefaction, and subcooling. Subcooling generally in Joule-Thomson valve to get the minus 160 degrees, because 160 degrees is the normal boiling temperature of methane. It means at 1 atmosphere is transported, the LNG is transported on ships at minus 160 degrees and 1 bar of pressure. There are other systems used to obtain low temperature, like, for example, Brighton cycles.
I was thinking about helium, maybe.
Helium. There are another because helium has a special behavior, has another system for its liquefaction. Another remark we have seen for the application, for example, in throttling valve, we said that the enthalpy is constant in throttling valve, and normally the temperature will decrease. But for some application in cryogenic, may the temperature in expansion, the temperature will increase. It depends. It depends on the temperature of the initial temperature. Joule-Thomson coefficient. It may be equal 0 or less than 0 or greater than 0. So if there is no question, we pass to the last part. So the last part is the non-conventional refrigeration system. You know that the problem occasioned by the utilization of refrigerants that damage the environment through ODP and GWP. We talked yesterday about this problem. So there are two tendencies. Using friendly refrigerants like hydrocarbons or natural refrigerants, or using another concept for the refrigeration. So we can use both. You can use new refrigerants or natural refrigerant. We can use the new technologies or consider other technologies, non-conventional technologies to produce cool. Among these technologies, there is the absorption refrigeration system. In a refrigeration system, in a simple refrigeration system, we said that is composed of condenser, compressor, and here an evaporator and a throttling valve. This is a simple refrigeration system like the system used for domestic refrigerant. And an absorption refrigeration, here the element that consumes energy is the compressor. So for an absorption refrigeration system, the elements are the same. Here there is a throttling valve, there is a condenser, evaporator, and the mechanical compressor here is replaced by a chemical compressor or thermal compressor. It's composed of generator, and absorber. So what happened when vapors issued from the evaporation obtained here, they are mixed with another fluid. Here we use a couple of fluid. We don't use one fluid. Here there is just one fluid. For example, we use here ammonia, but here we use two fluid. For example, we use ammonia plus water. So here the vapor will mix with water and the solution will pump it to the generator. The generator, we need some heat, for example, from the sun, waste heat from an engine, waste heat from another process, industrial process. When we heat this solution, vapor ammonia is liberated, and it is condensate and it follows the cycle. And the other water is returned to the absorber. So this is the difference. This element which use only few energy to drive the pump to replace the conventional compressor in refrigeration system, in vapor compression refrigeration systems. So it may be used here, heat, we need heat, maybe from sun, maybe from waste heat from an industrial process like engines, like turbines, like other processes. Another system, this is the refrigerants used. Generally, we use ammonia with, with water, and there is another couple of refrigerants, lithium bromide with lithium with bromide, lithium bromide with water. So here the refrigerant, if you use ammonia, the refrigerant is ammonia, so we can reach negative temperature. For the second one, lithium bromide water, we must operate with temperature, positive temperature. Another system used for the for refrigeration is the vortex tube. The vortex tube, here vortex tube. It is composed of a vortex here, a vortex chamber, an inlet, a vortex chamber, and a hot tube here, a cone-shaped valve, and a tube for the cowl. So it needs compressed gas. For example, air at compressed air, it enters from here, it undergo a vortex, and the vortex here, for when it arrives here, so the hot gas of the periphery will escape from the valve, from the periphery of the valve, and the core of the fluid is returned back as cooled. So compressed air is enter here, and we get hot air here and cold air from this side. We used this this concept. I have used in many PhD theses that I supervised. This vortex tube that has been designed by a Turkish team, dancer, Baskaya, know him? Turkish from a university, I don't remember, from a university in Turkey. They designed this vortex tube to work with air, and they designed, this is the vortex chamber to create a vortex. And we try to understand why we obtain cool from another part, a cooled stream from another part, and a hot stream from the other part. So we have here the variation of the kinetic energy for kinetic energy of the cold here, and the kinetic energy of the hot here. So it means that the reason is the exchange between energy between the core of the fluid and the periphery of the fluid. There is an exchange of energy. This energy is decreased, and this energy of the hot is the cold is increased. So there is a conservation of energy. The decreased energy go to the increased energy. And it is interesting to see here that when the energy, the kinetic energy of the hot part equal to the kinetic energy of the cold, there it is around 0.3. And around 0.3, we found that it is the optimum performance of the vortex tube. Here we can see it. It is for this one, for the red. It is about 0.3. Is the fraction? Is the fraction? Is the mass flow rate? The cold mass flow rate by the inlet mass flow rate.
And how do you calculate eta? Eta is efficiency?
Of mass flow rate.
What's eta? Why is
Isentropic efficiency.
Isentropic?
Because it is an expansion. We can do it for performance. We can calculate isentropic performance. In this work, we have calculated the isentropic efficiency.
There is no coefficient of performance.
There is coefficient performance, but in this work we have calculated only in another work we have calculated the coefficient of performance.
How do you define it?
The cooling is the coefficient of performance is the cooling effect obtained here. Cp T inlet minus T cold divided by the energy used to compress the air. Any question?
Could you explain the previous one again? Could you explain the previous one again? The one before this one.
This? Yes. Here we tried, in the last work we have done, we tried to understand what happened. Why there is this production of cooling from a part and hot stream from another part. So we calculated the kinetic energy. The kinetic energy here for the cold and the kinetic energy for the hot stream. So we know if we apply the first law of thermodynamics, its energy is conserved. So kinetic energy that leaves the particle, the cooled, the hot particle is gained by the cold particle for conservation.
So how much balance mean? What is balance?
The balance?
Yeah.
For energy is conserved. So for the kinetic energy, here, the kinetic energy of the hot is decreased. It is given to the cold. It is given to the core of the fluid.
So cold minus hot is balance, correct? How about the black one? PE in? Is it the energy supplied? Kinetic energy in?
At the inlet. At the inlet. until it is quasi constant. And here we did it here for the three pressure. I represent here only one pressure, and the three pressure are here for the isentropic efficiency. Just to show you another application. Carbon dioxide is also transported by ship, and we have the problem of boil-off. So in this work, I have done with a master, and I'll present it on the next ICR in Montreal. So I have done an exergy analysis of a liquefaction system of the carbon dioxide on board ships. So here the system, boil-off, yes. Here the tank of liquid carbon dioxide, and the boil-off, the vapor that could be generated here is driven by a compressor, then cooled in an intermediate cooler here, then compressed from 3 to 4 here, another compressor, then cooled here, and returned through a throttling valve as a liquid to the storage tank. So this system use only, we don't need to use another system. CO2 is, we use only CO2, because there are some applications that use another system to cool CO2. But here, CO2 is cooled and liquefied and returned to the storage tank. So we can, this is the balances, mass balance, energy balance, and here the exergy balance. For energy balance, inlet equal outlet, but for exergy balance, inlet equal outlet plus exergy destruction. And we can get the, for every element, every component of the system, equation for mass balance, energy balance, and exergy balance. And for energy balance, we can calculate the coefficient of performance. And for exergy balance, we can calculate the total exergy and individual exergy losses and the exergy efficiency. Here we have used the HYSYS, which is a process simulator. Because why? Because we have worked with a company, Algerian company, and they have a license for using HYSYS. This company is Safir SPA. It's a part of the Sonatrach. Sonatrach is the company of oil and gas in Algeria. Any question?
Load in Vortex Tubes, I mean, in watts, kilowatts,
The
compare Vortex Tubes and the traditional cooling systems.
the problem is the low performance. We can't use it, and it needs the compressed gas. It means that for compressed we have to use a compressor. So when we have, for example, in an industrial application, when we have a compressed gas, we can use it economically, better than conventional systems.
What is the amount of cooling load?
The amount of cooling,
Cooling load. I mean,
it can reach at minus 60, minus 70 degrees.
in capacity, cooling capacity.
In cooling capacity, we can calculate it.
For example, if you compare to a refrigerator, can it achieve the same thing?
No, no, no. The coefficient of performance is lower. It is lower than conventional systems. This is the problem for non-conventional systems. All non-conventional systems have coefficient of performance lower than the vapor compression systems.
I have a fundamental question. Why do you need to use such complicated mixtures? You have like 4 components in the system: propane, ethane.
For Cascade,
For Cascade.
the Cascade,
To be that complex.
the Cascade system was abundant because the cost.
No, I'm asking for that for liquefaction.
For liquefaction,
Your working fluid was a complete one.
for natural gas,
Yeah, for natural gas.
for natural gas, I said that the first one was the Cascade system. And the Cascade system, if we see, there are many turbo machines, compressors, turbines, and the cost of the system will be for the same capacity will be greater than the other technologies.
My question is the working fluid.
The working fluid,
Yeah, the fluid is a mixture. Why?
a mixture to attain the characteristic, to attain the temperature. A mixture. We use a mixer to attain the temperature of minus 160. We can't attain with the fluid, normal fluid, not a mixture. We can't. For example, for the Cascade, there is propane, then ethylene, then methane. We can't use propane to get minus 160. It changes to solid at this temperature. And we can't use, for example, methane for pre-cooling, because its temperature of critical temperature is low.
For air stage, there is
Another fluid.
That's for Cascade.
For Cascade,
but for Linda Hudson, you use the fluid itself. I mean, if you are trying to liquefy natural gas, then you use natural gas.
yes. Generally, Linde-Hobson and the Claude cycle are used for industrial gases, oxygen, hydrogen, argon.
Wouldn't you use freon instead of methane and methylene? Also, freon reduced up to minus 70.
Which fluid?
Freon.
Fluor?
One of the freons.
Components of fluors. The problem with synthetic refrigerants, the problem is their impact on the environment. So, for example, when they replaced CFC by R134, it was excellent as a replacement. And after some years, there has been another problem with the GWP. So 1 gram, I said the 1 gram of R134A, it's equivalent 1 kilo, 1.3 kilo of carbon dioxide. So in refrigeration, there is problem with the refrigerant. The best option is to use natural refrigerants. Maybe I go for student on the application of cool pack, for example. So here it means there are many parts. This is for thermodynamic properties. And this is all for secondary refrigerant, and this one for cycles, for systems. For example, here we have single stage and 2 stage for CO2 transcritical cycle and a 2 stage transcritical cycle. We go, for example, for the first stage here. We must specify cycle specification here. We enter evaporation temperature, condensation temperature. If there is subcooling and superheating, and pressure drop in the component, and we choose the refrigerant here. We choose the refrigerant among the refrigerant that are available in the software. For example, R290 is propane. And then we choose the cooling capacity. I said that in the data we need evaporation temperature, condensation temperature, and the cooling capacity. And we can calculate, we get the coefficient of performance. And we get, for example, state points, the different parameter of the point 1, 2, 3. So you maybe use this software, use another software. For example, for points, you may have different value for entropy. It depends on the reference state. Because the reference state is arbitrary, you may have different values of the enthalpies, but you will have the same coefficient of performance because coefficient of performance is calculated using difference of enthalpies. We can use another cycle, for example, Cascade. That is the Cascade, the high pressure here, the low pressure here. In the specification, we must do for the high pressure, the low pressure, 2 temperature, evaporation temperature, condensation temperature. Then we give the cooling capacity of the high pressure side and the low pressure side. Then we can calculate to get the coefficient of performance. And the other parameters like mass flow rates and volumetric mass flow rate, all what you need for the design of a refrigeration system.
Are we done? Are we done with the presentation? Is that all of it?
Yes, yes.
Thank the speaker for his presentation.
Thank you.